In this lecture, we'll talk about graphs of equations in two variables. Throughout this course, we're going to talk about different methods of graphing equations. The first method, which we'll talk about in this section, is to graph equations by plotting points. By definition, an equation in two variables, x and y, is a statement in which two expressions involving x and y are equal. A point is going to be part of the graph of that equation if it satisfies the equation. So, for example, we want to determine if the following points are on the graph of the equation: y equals x cubed minus 2 times the square root of x. The points are 0, 0, 1, 1, and 1, negative 1. Now remember, these points will be on the graph of the equation if, when we plug them into the equation, we get a true statement. Let's start with the point 0, 0. Our x-coordinate is 0, and our y-coordinate is 0. So we'll plug 0 in for x and 0 in for y, giving us 0 equals 0 cubed minus 2 times the square root of 0. Now we want to simplify and see if this is a true statement. If we simplify, the left-hand side stays 0, 0 cubed is 0, and 2 times the square root of 0 is 0, so we have 0 equals 0 minus 0, which of course is true, so this point is on the graph of the equation. Now let's look at the point 1, 1. Our x-coordinate is 1 and our y-coordinate is 1, so we'll plug 1 in for x and 1 in for y, giving us 1 equals 1 cubed minus 2 times the square root of 1. If we simplify that, we get 1 minus 2 times 1, and so 1 equals 1 minus 2, but 1 minus 2 is negative 1, so this is not true. 1 does not equal negative 1, so this point is not on the graph of the equation. And finally, we'll check out the point 1, minus 1. In this one, our x value is 1, our y value is minus 1, so we plug 1 in for x and minus 1 in for y, giving us minus 1 equals 1 cubed minus 2 times the square root of 1, which if we simplify gives us minus 1 equals 1 minus 2 times 1. So minus 1 equals 1 minus 2. Well, 1 minus 2 is negative 1, so this is a true statement, which means the point is on the graph of the equation. So now that we know how to determine whether a point is on the graph of the equation, we can talk about graphing an equation by plotting points. First, a little bit of terminology. For an equation that is solved for the variable y, for example, y equals 3x plus 2, the variable y is known as the dependent variable because its value depends on the value of x, and x is called the independent variable. So, to graph an equation by plotting points, we're going to select several arbitrary values for the independent variable, usually x, and use the equation to find the corresponding y values. This will create a series of ordered pairs, which we can then plot. Let's look at an example. We want to sketch the graph of the equation y equals x minus 6 by plotting points. So we'll draw a set of axes on which we'll sketch the graph, and we're going to make a table over to the left to represent the points we're going to plot. To determine which points to plot, we're going to pick some arbitrary values of x in the left-hand column, and y will equal x minus 6 in the right-hand column. So for our arbitrary values of x, I'm going to choose negative 2, 0, 2, 4, 6, and 8. It's a good idea to get 4 or 5 points that vary between positive and negative values, and use those to create your graph. And now we'll need to find out what the corresponding y values are. So when x is equal to negative 2, I can plug negative 2 into the equation x minus 6. Negative 2 minus 6 gives us negative 8. So I can plot the point negative 2, negative 8 on my graph. When x is equal to 0, 0 minus 6 gives us negative 6, so y is negative 6, and we can plot 0, negative 6 on our graph. When x is equal to 2, y will be 2 minus 6, which is negative 4, and we can plot the point 2, negative 4 on our graph. When x is equal to 4, y will be 4 minus 6, which is negative 2, so we plot the point 4, negative 2 on our graph. When x is equal to 6, y is 6 minus 6, which is 0, so we plot the point 6, 0 on our graph. And finally, when x is equal to 8, we'll have y equals 8 minus 6, which is 2, and we plot 8, 2 on our graph. So the final step to sketch the graph is to take these points that we've already put on the graph and basically just connect the dots. So the graph of y equals x minus 6 will look like this. So now that we've talked about sketching the graph of an equation by plotting points, let's talk about some of the characteristics of a graph. First, we're going to talk about intercepts. There are two possible types of intercepts. The first is the x-intercept, and that's the point or points at which the graph intersects the x-axis. Note that at the x-intercept, the y-coordinate will be equal to 0. And the second kind of intercept is the y-intercept, which will be the point or points at which the graph intersects the y-axis. At the y-intercept, the x-coordinate will be equal to 0. So for example, we can find the intercepts of a graph graphically. So we have a graph presented here, and we want to find the x-intercepts. Remember, the x-intercepts will be where the graph crosses the x-axis. So that occurs at 2 and negative 2. So when x is 2 or x is negative 2, those are x-intercepts. But remember, the intercepts are points, so we need to write them as ordered pairs. So the x-intercepts for this graph will be the point negative 2, 0 and the point 2, 0. Now let's find the y-intercept. Where does the graph intersect the y-axis? It appears to intercept the y-axis when y is equal to negative 3. So our y-intercept will be the point 0 minus 3. If we don't have the graph of the equation, we can also find the intercepts algebraically. So for example, let's find the intercepts for y equals x squared minus 9. We'll begin by finding the x-intercepts. Remember, when the graph intersects the x-axis, y is equal to 0. So for x-intercepts, y will be equal to 0. So we can plug 0 in for y and solve the equation. Plugging 0 in for y, we get 0 equals x squared minus 9. We can factor x squared minus 9, giving us 0 equals x plus 3 times x minus 3. Using the zero product property, that means that 0 equals x plus 3 or 0 equals x minus 3. We can solve each of these to give us x equals negative 3 or x equals positive 3. But remember, our intercepts are points, so we need to express them as ordered pairs. So our x-intercepts will be the points negative 3, 0 and positive 3, 0. Now let's try to find the y-intercept. Remember, to find the y-intercept, x is going to be equal to 0. So let's plug 0 in for x. That gives us y equals 0 squared minus 9, which, if we simplify, gives us y equals negative 9. Again, our intercept is a point, so we need to write this in an ordered pair. So the y-intercept will be the point 0 minus 9. Let's do another example. We want to find the intercepts for the equation y equals 3x minus 9. I'd like for you to take a few minutes and see if you can identify the intercepts on your own. After you've gotten an answer, continue the lecture. So for the x-intercept, we'll set y equal to 0, which means 0 equals 3x minus 9. We can add 9 to both sides of the equation, so 9 equals 3x. And then to solve for x, we can divide both sides by 3. So we get 3 equals x. Again, the intercept should be an ordered pair, so we can rewrite this using ordered pair notation. And our x-intercept will be the point 3, 0. Now we try to find the y-intercept if it exists. For the y-intercept, x will equal 0, so we plug 0 in for x, giving us 3 times 0 minus 9. If we simplify that, we get y equals negative 9. So our y-intercept will be the point 0, negative 9. Another characteristic of graphs is that of symmetry. There are three types of symmetry in graphs. The first is symmetry with respect to the x-axis. A graph is symmetric with respect to the x-axis if, for every point xy on the graph, x minus y is also on the graph. So we have a graph here that is symmetric with respect to the x-axis. So what we can see is that the x-axis acts as a mirror. What's above the x-axis looks the exact same as what's below the x-axis, only in different directions. The second type of symmetry is symmetry with respect to the y-axis. A graph is symmetric with respect to the y-axis if, for every point xy on the graph, negative xy is also on the graph. So here's a graph that displays symmetry with respect to the y-axis. Note that any point xy and has the point negative xy there also, and the y-axis acts as a mirror in this case, so what we have on the left side of the graph is a mirror image of what's on the right side of the graph. The third type of symmetry is called symmetry with respect to the origin. A graph is symmetric with respect to the origin if for every point xy on the graph, negative x negative y is also on the graph. So here is a picture of a graph that displays symmetry with respect to the origin. Symmetry with respect to the origin is also called rotational symmetry. And what that means is if you took the graph and you rotate it 180 degrees or turn it upside down, you would have the exact same graph. So symmetry with respect to the origin you can test by rotating the graph and seeing if you get the same thing. While you can look at a graph and tell whether or not it has symmetry, you can also test for symmetry without looking at a graph. We can test for symmetry algebraically. So, to test for symmetry with respect to the x-axis, we're going to replace the y variable with negative y and then simplify the expression. If it results in the exact same original equation, then we have symmetry with respect to the x-axis. To test for symmetry with respect to the y-axis, we'll replace x with minus x and simplify the expression. If it results in the exact same original equation, then it will be symmetric with respect to the y-axis. And finally, to test for symmetry with respect to the origin, we'll replace x with minus x and y with minus y and simplify. If that results in the same original equation, then we'll have symmetry with respect to the origin. So let's do an example to clarify this. We want to determine if the equation x squared minus y minus 4 has any type of symmetry. First, we'll test for symmetry with respect to the x-axis. We replace y in the equation with minus y, so that gives us x squared minus negative y minus 4 equals 0. We simplify that, x squared plus y minus 4 equals 0, and then compare it to our original equation. Since our result is not the exact same as the original equation, this does not have symmetry with respect to the x-axis. Next, we'll test for symmetry with the y-axis. Replace x with minus x, so we have minus x quantity squared minus y minus 4 equals 0. If we simplify that, minus x quantity squared is the same thing as x squared, so we get x squared minus y minus 4 equals 0. And we compare this to our original equation. Since the resulting equation is the exact same as the original equation, we have symmetry with respect to the y-axis. And finally, we'll test for symmetry with respect to the origin. We replace x with minus x and y with minus y, giving us minus x squared minus negative y minus 4 equals 0. If we simplify that, we'll get x squared plus y minus 4 equals 0. We compare that to our original equation, and we see that it's not the exact same as what we started with, so we do not have symmetry with respect to the origin. This means that the equation x squared minus y minus 4 equals 0 is symmetric with respect to the y-axis only. So let's try one final example. Again, we want to determine algebraically the symmetry of the equation 4x squared plus y squared equals 8. I'd like for you to take a few minutes and try to figure out whether this has symmetry with respect to the x-axis, y-axis, and/or origin. Once you have your answer, continue the lecture. So we'll start by testing for symmetry with respect to the x-axis. We replace y with minus y, which gives us 4x squared plus minus y squared equals 8. If we simplify that, that gives us 4x squared plus y squared equals 8. And since that's the same as the equation we started with, we have symmetry with respect to the x-axis. Next, we'll test for symmetry with respect to the y-axis. We replace x with minus x, giving us 4 times minus x squared plus y squared equals 8. When we simplify, that gives us 4x squared plus y squared equals 8. And since the resulting equation is the exact same as the equation we started with, we have symmetry with respect to the y-axis. Finally, we'll test for symmetry with respect to the origin. We replace x with minus x and y with minus y, giving us 4 times minus x squared plus minus y squared equals 8. We simplify the equation, giving us 4x squared plus y squared equals 8. And again, since the resulting equation is the exact same as the equation we started with, we have symmetry with respect to the origin. So, the equation 4x squared plus y squared equals 8 is symmetric with respect to the x-axis, the y-axis, and the origin.